In this session, we'll discuss about the energy consumption and solar radiation spectrum. Okay, so to begin with, if you see the global energy consumption, you can see the most of the energy is produced. So first of all, the units. So this is given in terawatt hour, right? And it is measured in a year. I mean, throughout a year it is measured, and this is what it is given here in the y-axis. And you can see that from 1800 how this energy consumption has increased, and you can see it's exponentially, it is increasing day by day. It's because it's due to the population, again population increasing day by day, and also the human lifestyle, right? So it is increasing day by day. So to live with a higher lifestyle, we need energy. And where does this energy comes from? So if you consider at this year in 21st century, so most of the energy, you can see that they come from, so this is in 2019, but it continues more or less similar fashion till today. So most of the energy comes from coal and this oil, and then comes from the gas, natural gas. And in this chart we are not considering the energy coming from food. Like all human beings or animals, we get energy from food, so this is not counted here in this chart. So interestingly, you can see that these are all coal, oil or natural gas. They are not abundant. But whereas in the top you can see the hydropower, wind, solar and other renewable energies, and modern biofuel. Okay, modern biofuel, we leave it. So hydropower, wind, solar and other renewable, like we have this tidal power, right? So these are the energies which are renewable. It can be regenerated or refilled by the nature within a short span of time. Like coal also, you can think that we can get back from nature, but it takes a lot of time to produce a new coal, right? It's not reasonable. It doesn't come under this renewable, that's why. So and if you see the consumption of energy, it is increasing tremendously as time going on. Now see the economy or the price of a product. So it depends on supply and demand, right? So any product, if the demand is much higher than the supply, obviously the price increases. So same case it falls for energy or the electricity as well. So we need to think about really the higher production of energy because of the demand, right? So we need to match that to have a consistent price. So for that, coal, oil and natural gas, we are bound. We cannot do much on them. We are basically running out as days are passing by. But we can really focus on the other renewable energies. And if you see the research or the trend, it is really increasing with time. But we need to work even much higher rate, I mean, on using these renewable energies. Like if you see the hydropower, it has increased a lot, wind as well, and the solar energy also, it is increasing very fast, right? So we discussed more about this solar energy in the previous class, that how other countries and how it is getting developed with time. Now we understand that the importance of this renewable energy, right? So let's see how all these different types of energies or source of energies, how they are interlinked. So at the end, we mostly use the most of the energy in electrical form, right? Because it is easy to transport and you can easily convert back into other form of energy. So the consumption of energy, if you think, most of it goes through electrical energy. So a nuclear power plant, let's say, so they work under nuclear fusion, right? So it generates a lot of heat, and then with that heat basically you run a turbine. So with that thermal power you basically boil water, make steam, and then you convert into mechanical energy. So you have losses there also. So heat engine, it basically follows Carnot's efficiency, right? So Carnot engine, there modern all heat engines are followed with Carnot heat engine. So efficiency is less than 60%. And then from mechanical to electrical energy conversion, we use these turbo generators or turbines. So there we have efficiency about 90%. And then electrical energy, we consume it for all different purposes. Now if you come for chemical energy, so all this coal, oil or gas, biomass or even hydrogen, they are all chemical form of energy. So again we need to convert this chemical energy to most of the cases to thermal energy. So there you get efficiency of about 90% for coal, oil and gas. And then same process, thermal energy, you use a Carnot engine, mechanical, then you use the turbine for electricity. Or you can use chemical energy to direct electricity by using, let's say we have this hydrogen, so you can run a fuel cell. If you have not heard of fuel cell, I suggest you to read at least the basic of it, how do they work and all. So these fuel cells basically they can convert directly this hydrogen energy from electricity to electricity. So this is another way of converting into electricity, and you can store the electrical energy, the extra electrical energy, as a form of chemical energy, right? You can store it. Let's say you are generating more electrical energy, you can store it in a battery. That is also you're storing in a chemical form. Or if you want to store more electrical energy, let's say for some reason you are generating more electrical energy than the consumption, this is not a very suitable way to store it in a chemical form, because you need use battery bank or something, right, to store it. Rather you can store it in a gravitational hydrotidal way, like so in that way what we generally do, whatever the excess electrical energy we have, we run some pump. So run some water pump and put the water which is there in lower height, we pump it to a higher potential energy, or much higher height. So we are storing the energy as gravitational energy. So we pump the water at lower height to a higher height. So we can store that water at much higher height, and then when we need electricity we can release that water, like we do in dam and other tidal thing we have, right? So we basically release the water and we run some water turbine to convert into mechanical, and then we convert into again electricity. So you understood the concept of storing electrical energy. So there are ways to store. One is chemical, you put it in battery, or you can store it in gravitational or gravitational potential energy, basically water. And then wind energy. So this is one clean energy, that wind kinetic energy. We can use it to produce electricity, right? You might have seen that big windmills, right? Even in our area near this Penikunda we have windmills. If you ever visited, it's very nearby here, so you can go there and visit sometime maybe, or yeah. So the wind kinetic energy also can be converted into mechanical energy, right? So you run basically very big fan kind of thing, basically windmill we call them, and then that mechanical energy you use again turbine or turbo generators, and then convert into electricity.
Sir, the AC power generated is not stored anywhere, right, sir?
AC power, the grid we generally don't store, consume as it is. If the consumption level, let's say it is less, let's say in the early morning we need very less energy, so that time we shut down some of our grid production, some of the grid this thermal point we just shut down, but we don't store this AC electrical energy as such. But renewable energy, if it is you are producing more, we store them with this gravitational hydrothermal way, gravitational this way that we pump the water into higher altitude. Okay, so we are at wind, and next is the gravitational. I'll just tell again this one. So in the some place like mountain area and all, there are a lot of rainfalls and all, right? Or even by natural also, some mountains are there and some water bodies there, so we can release those water in a controlled fashion, and we can run some mechanical turbine and convert into electricity. So this is very much used in the country Brazil, like they use a lot this hydro electricity. Or even the tidal, like in the sea we have a lot of tides, right? The movement of water, so you can fix the surface level turbines and you can convert into mechanical energy and convert them later to electricity. And the next is the last one is solar. So this is one of the easiest way, I would say. It just directly converts sunlight into electricity. No other form, no mechanical, nothing, just a silent, very silent and very easiest way, I would say, to get electricity from this renewable source of energy. And that's what most of the research nowadays, these are almost all stable, but solar energy, lot of scopes are there and people are working, and many groups are working worldwide to get better and better in this perspective. Now let's just one fun thing, like we are talking about energy, wattage and all, right? So what do you think the human energy, if the humans, right, we are also working, right? So what's the wattage of a human body? How much do you think could be for a human body? Say 10 watt, 100 watt, 1000 watt. How much do you think? Let's say we are sitting at rest, so we are producing heat, right? We have a basal metabolic rate, that BMR rate. So for a standard human, average human at rest, we produce around 100 watts of power. Now if you are walking, or if you are sprinting, or if you are doing a very high intense cardiovascular activities, you can even produce up to 2000 watts of power. So 100 to 2000 watt is normal range for human being, the wattage we can produce. Okay, so this is one just to show you the human body temperature, how it varies, like how you produce the heat in our human body itself. So so this is the back side of a human, and this project was done at this Stanford University. You can go to this link and find more details on it. So if you can see the variation of body temperature of a human, so here is the scale bar. 29 is the lowest, and you can see it is gradient with color, right? And 39 is the maximum. So the shoulder part or the head area is the most hot part in a human body. I mean, you can see the temperature range, and the back muscles and other, you can see the variation of temperature. So it depends on different kind of muscles, right? We have actually two types of muscles, right, in human body. One, we can move by our desire. Some muscles we cannot move as we want. I forgot the exact name for those, like the ears. It has muscles, but we cannot move by ourselves. But whereas our biceps, triceps, we can move with our wish, right? So yeah, so depending on the type of muscle, and also the position matters. So the body temperature varies, and total, if you're sitting idle, we produce around 100 watts, and the energy we are getting from all the food we consume, right? And again, if you go much deeper into food, and also the three different types, right? Carbohydrate, protein, and fat. Fat is the most condensed, not most condensed, most high energy density food, I would say. It contains more energy, right? The fat. Protein is the least, not protein is the least, carbohydrate is the least, and then protein in the middle. I forgot the exact number, but if you're interested, you can look into some biological books. But you should know the basic constituent of a food and how much energy we get from each of them, right, to live a healthy lifestyle. So this is all about the human energy converted, human energy we use in our daily life, and you can convert into electricity also. There are gyms and all, wherein you can go and work out and produce electricity. Like there are various gym equipments these days available. Like you paddle, you go to gym and do paddling, right? Those kind of bicycles, they are attached with turbines. So you sit there, you do workout, you produce energy as well. So coming to now solar radiation. So the most abundant energy, I would say, is the sun, right? So solar radiation, and the source is of course the sun. And if you go much deeper into the construction or the constituent of a sun, you will see that the outer part which we observe from Earth is the corona of sun, and then it has a chromosphere. And if you get inside deep, so this is all astrophysics people, they have divided the sun. They did a lot of this chromatography, this what is that analysis called, spectrum analysis and all they have done, and they have divided this like Earth we have divided, right, inside up to the core different spheres. So similar, the sun is also divided into different zones, and the main constitute of sun is again hydrogen and helium, right? And we all know the source of this energy from sun. You are getting it from nuclear fission, right? Nuclear fusion. So there are two things, fission and fusion. Fusion is combining, right? And fission is splitting up. Like for a nuclear reactor, it's a fission, but for sun it is fusion. So the source of energy for the sun, we are getting it at different steps. So it consists of four protons. They react to produce one helium core. So one helium core means two protons and two neutrons, right? And then it radiates to positron, to neutrinos, and electromagnetic radiation. So from the four protons, after the reaction, these are the products. You get a helium core, two positron. Positron is nothing but antiparticle of electrons, and two neutrinos, and the electromagnetic radiation. So this is what is important to us. Now how do you account this electromagnetic radiation? It's because of, again, the Einstein E equal to mc square, right? So whatever the positron, the positron, whatever it generates, it get annihilated with the electrons, leading to a additional radiation, but it will not be too much. But the main production comes from this one. The mass of helium core is 0.635% less than the 4 protons. So this mass we are losing, and this mass basically converted into energy by this Einstein famous equation, right, equals to mc square. So that's the source of energy from the sun. We are getting it. Right, now coming to the electromagnetic spectrum, as we are talking of, we should know all different types of, or different regions of electromagnetic spectrum. So the lowest energy one is the radio frequency, the one we use for our radio communication, or local this walkie-talkie and other things we use for short distance communication, right? And then we have microwave region, where this is the wavelength in meter. So it is radio wave is 10 to the power 3 meter, 10 to the power 3 meter. So it's like 1 kilometer, the wavelength. It's a really long wave length of the signal. So that's why you can see that radio wave, it can that's why it has a less range. Basically it can easily get abstracted with object. Sometimes it helps also, it can bend towards through a building. That is one plus point, but negative point is the absorption. The absorption will be too high, so it cannot propagate very high, very long distance. And then we have microwaves, which is 10 to the power minus 2 meters. Then we have infrared. So, and here is the physical comparison of the size. You can feel it. So microwaves comes in 10 to the power minus 2, its size of a butterfly, and then the wavelength. And then infrared, it is 10 to the power minus 5 meter, right? So it's like in tip of the needle. It's really tiny, getting tinier. So as the wavelength is decreasing, frequency is increasing, energy is increasing. We all know the basics of it, but you should remember the range. And then comes the visible range. So visible is, the wavelength is about 10 to the power minus 6 meter, and the frequency also corresponding, if you see, it is 10 to the power 15. So you can always convert back, right? C equals to lambda nu. From there you can always convert back onto other. As all electromagnetic radiation, it travels in speed of light, whatever the range it is in a free space. The speed is constant, right? Okay, so visible. And then comes ultraviolet. So ultraviolet falls in 10 to the power minus 8 meter. It's like a molecule's size, and the frequency, you can see, it is already 10 to the power 16 range, 10 to the power 16 hertz. And then X-ray comes. The wavelength is 10 to the power minus 10 meter. It's getting really tinier. You can see it's the size of an atom. The frequency goes 10 to the power 18 hertz. And then comes at the end gamma rays. So gamma rays are the most highest energy, I would say, they carry, the gamma photons or gamma radiation. The frequency is 10 to the minus 12, wavelength is 10 to the minus 12 meter, and frequency is 10 to the power 20 meters. And the size, it's atomic nuclei size. So with this, you can also compare that, you may correlate, like, why do you use X-ray to see material structure, right? Why do you use UV cameras to see molecules? Or why do you use a visible microscope to see all the bacteria or our blood cells and all? right? We know this optical limitations and the diffraction limitation and all, right? So you can correlate the wavelength and with the size of the particle or the material. Now coming to the radiometric properties. So how can you measure or how can you quantify an electromagnetic radiation falling on a surface, right? So in this, a surface A is irradiated by a light from various directions. So practically that's what it happens, right? Any surface or any, let's say you're reading a book, so the light is coming from all different directions, right? Reflected from the wall, directly from the lamp, or direct from the outside window. Now if you want to quantify the total radiation in that surface, it depends on basically the area you are considering, the total we are trying to calculate the total optical power. So the power is totally it depends on two factors. One is the area of the area we are considering of, and another is the solid angle, the radiation at what solid angle we are covering up, right? So we need to integrate these two things. So one integration is over area, another integration is over the solid angle. So mathematically it is done with this LE cos theta d omega dA. So d omega is again sine theta d theta dq. So we'll get back this terminology is much more detailed later. Okay, so the quantity Le is called the radiance. It's a fundamental radiometric properties of a, if you increase the area of your interest, definitely the total power will increase, and the solid angle also, right? So from what angle the light is coming from, definitely it matters, right? So coming to the solar energy spectrum, let's discuss a little bit more generalized way, then we'll get into those mathematics. So if you see the solar spectrum, so how can you first of all record this solar spectrum, right? So you should have a spectrophotometer to record it. Like each wavelength you have to scan and see the irradiance level, that is the energy present at that particular wavelength. I mean, cannot directly get it, right, this spectrum. So you should have a spectrophotometer where you can scan the wavelength of your interest. So as you can see, the solar radiation, it ranges from about 250 or a little lower, 250 nanometer to it goes until 250 2500 nanometers. In this range all the photons basically falls in. Out of that we have basically three regions: UV, visible and infrared. So UV is again the best way to okay, so UV we consider from 150 to 380 nanometer, and then visible is 380 to 720, and rest is 720 to above is IR. So that's what we divided into, and you can see the most of the energy is falling in this three region: UV, visible and IR. So in the visible region we have the maximum energy 380 to 700, we have about 48%, and then IR we have 43, and UV is just 7.2% only, and others like above 4000 nanometer we have just 1%. So how do you arrive this percentage? This is very simple, right? We can just integrate the curve within this wavelength, and we can, so basically the area under this curve in this region will give you the total energy, right? And then you normalize with 100%, you can calculate it. Now in this curve you are seeing that there are three different curves, right? One is this black solid line, one is there this yellow one, and then inside there is a red one. So the black solid line represents a black body radiation which has a temperature of this one 5778 Kelvin. So this is a again simulated black body radiation. You can do it yourself also, a simulation for a black body radiation by using this Wien's displacement law. And if you consider the sun as a black body, then sun temperature would be this one. So that's why we put this curve for a comparison. And then the yellow one is the sunlight radiation above the atmosphere. So above atmosphere, if you record this spectrum, you will get this yellow curve. It's very close to this black body radiation. And if you measure in the Earth's surface, you get the curve of this red one, whereas you can see there are a lot of absorption happening, right? Because the photons or the solar radiation, it has to travel the Earth atmosphere, right? And in the atmosphere we have various gases, molecules, right? Like we have water, absorption due to water, absorption due to oxygen, absorption due to ozone, and then absorption due to carbon dioxide. So these are the major absorption process happening in the atmosphere. So you may hear that might heard this importance of ozone, right? You can see that ozone, it is absorbing in this UV range. So that's the importance of ozone in our atmosphere. So they absorb the harmful UV radiation, and you can see the yellow one is above atmosphere, and after this ozone absorption, you can see most of the UV radiation is cut or got absorbed with this ozone layer. Still there are some part, so that's why you get all this sunburn and all if you are exposed for a longer duration in the sunlight, right? Now coming to the application of solar cell, this radiation spectrum is very important, right? Because this is our final source of energy, these photons. So we need to design solar cell accordingly that we can trap or you can utilize these available photons. So we should not make or choose a solar cell which will absorb this range of photons, right? Because there is no photon present at all in this about 1300 or 1400 nanometer. We don't have any significant number of photons, so we'll avoid constructing solar cell in this range. So the best possible way to make solar cell in this visible region, you can see that most of the photons are falling in this range, and also in the IR also we have a good number of photons. So we'll get into the detail of the construction of solar cell and how you can trap different range of photons with different band gap of the material. Okay, so you understood this radiation spectrum. This is very important, and if you want to do it yourself, like if you want to get this curve yourself in an experiment and see it, it's easy. I mean, we need just a spectrophotometer, and if you're in campus, we have spectrophotometer. We can run this experiment very easily and get this result. Not this yellow one, then we have to take a plane right above the atmosphere to record this, but the red one we can easily do it in the lab. And nowadays very tiny portable spectrophotometers are available, which scans this wavelength in a blink of eye. Basically it measures the whole spectrum simultaneously. Nowadays those compact semiconductor spectrophotometers, they measure the whole range simultaneously. So if you're interested to little bit of learning this spectrophotometer, it's good to learn also, know at least. Okay, now coming to this concept air mass. So this concept of air mass is coming because the solar radiation spectrum is not constant throughout the geographical position of Earth, right? So someone is doing, let's say, research in India. Even in India it changes, right? The radiation, solar radiation, it depends on the longitude and latitude of that position, and also it depends on the weather of that day, right? The radiation spectrum, it highly depend on weather and longitude and latitude of that place. So we need to standardize this energy spectrum to carry out the research work, or to claim some of your result. So that's where comes this air mass. So the air mass is the path length which the light takes through the atmosphere normalized to the shortest possible path length. That is when the sun is directly on the overhead. So when the sun is directly on the overhead position, you can see the amount of air column it needs to travel is the least one, right? And as it made some angle with this zenith, we call it as zenith angle. So as this theta increases, the radiation has to travel more and more air column, so more and more absorption, right? And we lose basically in the exact intensity, or the intensity it used to get. So when this theta is 0, that is at the vertical zenith angle, this is called air mass 1, and we define this air mass 1 as 1 by cos theta. Okay, so 0 cos 0 is 1, so AM is 1. Now let's say we move to 60 degree, so 60 degrees cos 60 is half, so we'll get air mass of 2, right? Now you need to make a standardization. So 1 you will get in the equator. As you change the latitude, this theta changes, right? So as I said, at 60 degree, this 60 latitude, so the AM will be 2, so it will change according to the location. So for that purpose we put a standard on this solar radiation. So that is what we called as AM 1.5G is the standard solar spectrum on Earth's surface. So this is done with the research group, so that throughout the world we follow this AM 1.5G, which is equivalent energy is 1 kilowatt per meter square. So this is one okay, just a typical diagram, a schematic, where you can have a feel of that, that how the intensity will change as you change the angle. You can do this experiment by yourself by holding just a torch light and see it, right? If it is directly vertical on the paper or the table, you get the highest intensity. As you change the angle, make it oblique, basically you are increasing the area, so obviously the intensity or the area per unit, energy per unit area will decrease as you change the angle, right? So same case follows for Earth and Sun. So that's why we use this standard value. But this G stand for the global, so it's a global constant. Now we can have an artificial this is called solar simulator, because from sun, or if you expect from sun to get 1 kilowatt per meter square, it is not possible. Right now, today, the place I'm sitting, it's cloudy. I cannot do any experiment, right? Because 1 kilowatt per meter square is not available naturally. So what people do is they have created or designed artificial solar simulator. It is nothing, it's an halogen bulb. So if you see the radiation spectrum of a halogen bulb, it's very close to, it comes very close to this black body radiation. Okay, this absorption peaks will not be there, right? You're using a halogen bulb, but more or less the average will look like this spectrum. So that's why practically we use a solar simulator to do all this experiment.